There was a moment in 1942 when every RAF pilot knew they were flying the wrong aircraft. The Mitsubishi Zero had become a ghost in the Pacific sky, faster, more agile, capable of turns that defied the laws of physics. British Spitfires and Hurricanes, the machines that had held the line over England just 2 years earlier, were being outmaneuvered and destroyed with mechanical precision. The reports came in daily. Another pilot missing, another squadron reduced, another silence added to the growing catalogue of British defeat. But the silence wasn't just over the Pacific. It had invaded the design bureaus of Southampton, the engine shops of Derby, the drafting rooms where young engineers stared at blueprint after blueprint, searching for an answer that seemed to slip through their fingers like smoke. This is the story of how a problem without a solution found its way to the workbench of a man who believed the answer lay not in more power, but in understanding the invisible. Dr. Edmund Harcourt was 53 years old in the autumn of 1942 when he received a classified assignment that would reshape the trajectory of his life. He had spent 30 years studying the behavior of aircraft structures under extreme conditions. Stress fractures, metal fatigue, the way materials sang their warnings before they broke. His reputation was solid, methodical, respected in circles where precision mattered more than ambition. He had never sought prominence. He had only ever sought truth. The assignment came through official channels, stamped with red ink, and delivered to his modest office at the Royal Aircraft Establishment in Farnborough. The message was stark. Why does the Japanese fighter maintain its performance in sustained maneuvers? What structural advantage permits continuous acceleration without structural degradation? In other words, how was the Zero built to do what it should not be able to do? Harcourt was given access to the remains of a Zero that had been shot down over Burma 6 months earlier and recovered by British intelligence. The aircraft had been partially disassembled, photographed, and locked in a secure hangar at RAF Bentley. He was permitted to examine it twice weekly, always under supervision, always under pressure to produce answers the Air Ministry desperately needed. On his first inspection, Harcourt noticed something that other engineers had overlooked. The structural integrity assessments had focused on obvious elements: wing geometry, fuselage thickness, engine displacement. But the Zero's aluminum, the very skin of the aircraft, was behaving in ways that contradicted established material science. Under comparable stress loads, British aluminum would have shown visible deformation. The Japanese aluminum appeared almost immune. He spent weeks consulting metallurgical records, cross-referencing manufacturing techniques, studying historical reports of Japanese industrial practices. The data was fragmented, often contradictory. Japanese production methods remained largely unknown to British intelligence. But there were hints, scattered references in intercepted communications, fragments from captured engineers, mentions of heat treatment processes that Western industry had abandoned as impractical. Harcourt became obsessed. His wife, Margaret, noted in her diary that he had begun arriving home at irregular hours, his shirt cuffs stained with metal filings and graphite, his mind clearly engaged in problems he could not discuss. She was accustomed to this. They had been married 28 years, and his silences had long since become a language she understood. It was on a Tuesday morning in November, while Harcourt sat in his modest kitchen waiting for tea to brew, that the revelation came. He was holding a cup, ordinary English porcelain, white with a faint blue rim, and he noticed how the steam rose from the liquid in precise, repeating patterns. The heat distribution was uneven. The steam rose more vigorously where the ceramic was thinner, where heat conducted more efficiently through the material. He set the cup down very slowly. The Zero's aluminum was behaving like that porcelain. The Japanese had engineered a heat treatment process that created subtle variations in crystal structure throughout the wing panels. These variations acted as internal pathways for stress distribution, allowing the metal to flex and recover, without the catastrophic fatigue that plagued British designs. It was not stronger, it was smarter. The material had been taught to move with stress rather than resist it. The teacup sat on his table as evidence of a principle so simple, so elegant, that the entire Western aviation industry had failed to see it. Harcourt rose and walked to the telephone. He requested an urgent meeting with his supervisors. Within hours, he was presenting his theory to senior officers of the Air Ministry. The reaction was skeptical at first, then urgent. If this was correct, if the Japanese had developed a heat treatment methodology that enhanced material resilience through structural manipulation rather than raw strength, then British aircraft could be retrofitted. New designs could incorporate this principle. The technological gap could be narrowed. What Harcourt did not know as he made that telephone call was that his discovery had already been made. American engineers, working independently with captured Zero components, had reached identical conclusions. The intelligence would be shared within weeks. The knowledge would begin to reshape Allied fighter design by 1943, but the teacup on his table remained. Margaret washed it that evening and returned it to the cupboard. Harcourt never spoke of it again. The moment of revelation for him had already transformed into something else, into obligation, into urgency, into the machinery of war. The impossible machine had not been impossible at all. It had simply been better understood. Now I invite you to leave in the comments where you're watching from and the exact time you're listening to this story. We're interested in knowing how far these documented accounts travel, and at what moments of the day or night they reach you. The metallurgical tests began in December 1942, conducted in a secure laboratory beneath the concrete bunkers of RAF Bentley. Dr. Harcourt was given a team of 3 junior engineers and access to a sample of recovered Zero aluminum. Not much, perhaps enough for a dozen test coupons, but sufficient to begin systematic analysis. The laboratory was cold that winter. The heating system had been deliberately kept minimal to preserve the integrity of delicate instruments. Harcourt wore 2 wool jumpers beneath his white coat, his breath visible in the thin air as he moved between the testing apparatus and the observation station where he made his handwritten notes. The first tests were straightforward. Tensile strength measurements, compression tests, microscopic examination of grain structure. Nothing emerged to distinguish the Japanese aluminum from conventional specifications. The composition was nearly identical to British standards. The purity was excellent. The dimensions were precise. On every conventional metric, the Zero's wing panels should have performed no differently than RAF aircraft. But they did. When the team subjected the Japanese aluminum to cyclic loading, simulating the repeated stress of sustained turns and accelerations, the results violated expectation. The material showed what Harcourt termed resilience memory. After each stress cycle, the metal returned to its original dimensions rather than retaining microscopic permanent deformation. British aluminum, tested under identical conditions, showed cumulative damage. Hairline fractures appeared. Fatigue degradation was measurable and predictable. The Japanese metal appeared to heal itself. "It's impossible," said Lieutenant James Whitmore, the youngest member of the team, staring at the test data with obvious confusion. "Materials don't behave this way. There's no mechanism for—" "There is," Harcourt interrupted quietly. "We simply haven't named it yet." Over the following weeks, Harcourt theorized that the Japanese heat treatment created a deliberately engineered microstructure, zones of varying crystalline alignment that distributed stress across multiple pathways rather than concentrating it in vulnerable points. Under cyclic stress, this structure would shift slightly, allowing microfractures to remain isolated and non-propagating. It was not that the material was stronger, it was that the damage was prevented from accumulating. The implications were staggering. A British Spitfire experiencing the same turning forces as a Zero would see progressive weakening of its wing structure. After 50 hours of combat operations, critical components would be approaching failure thresholds. A Zero pilot could maintain extreme maneuvering capability indefinitely because the airframe simply did not degrade in the same manner. Harcourt wrote a technical memorandum detailing his findings. The document was 11 pages, densely technical, filled with metallurgical nomenclature and stress diagrams. It concluded with a single recommendation. British aircraft manufacturers must immediately investigate whether the identified heat treatment process can be replicated or improved upon. This represents not a minor advantage, but a fundamental restructuring of airframe design philosophy. The memorandum was classified most secret and distributed to 6 individuals within the Air Ministry. The response came within a week, an order to accelerate all research and provide preliminary recommendations for implementation within 3 months. 3 months was impossible. The entire British aircraft industry would require retooling. Factories would need to modify their heat treatment equipment. Specifications would have to be rewritten. Quality control procedures would need revision. Every engineer, every worker, every supervisor would need to understand new protocols. But war, Harcourt had learned, operated on a different temporal scale than peace. Impossibility was merely a bureaucratic category. He was assigned a larger team. A second laboratory was opened. New testing equipment was requisitioned. The urgency became physical, visible in the way supervisors moved through hallways, in the increased frequency of meetings, in the late-night telephone calls discussing production schedules and material allocations. By February 1943, preliminary recommendations had been drafted. A modified heat treatment protocol was proposed for Spitfire wing panels. The first production run was authorized for March. The protocol would be kept classified. No pilot would know that his aircraft had been subtly redesigned. No engineer beyond the immediate program would understand why the heat treatment schedules had suddenly changed. Harcourt found himself at the center of decisions that would affect the operational capabilities of thousands of aircraft. He had never sought this position. He had only followed the logic of materials, the physics of metals under stress, the information contained within a teacup's steam. But there was a cost to this knowledge. Harcourt began to understand late one February evening as he sat alone in the laboratory that he was now complicit. The Zero had been designed to kill RAF pilots. His discovery was being used to prevent that killing. Both were acts of war. Both were justified by necessity. Both had moral weight that no technical memorandum could adequately address. He looked at the remaining sample of recovered Zero aluminum, now depleted to a few small coupons, and he understood that he was holding the physical evidence of another nation's tragedy. Those aircraft had been flown by trained pilots. Those pilots were now dead, shot down by British fighters that were suddenly, fractionally, more capable of sustained maneuver. The material itself held no allegiance. It simply conducted stress more efficiently. If this story surprised you, make sure to leave a like to support the channel. The heat treatment facilities across Britain were not designed for precision work. Most had been constructed in the 1920s and 1930s when aluminum production was still an emerging industrial capacity. Furnaces were crude by modern standards, temperature controls were manual, and worker expertise was the primary variable that determined output quality. By March 1943, these facilities were being asked to implement a manufacturing protocol that demanded tolerance levels of plus or minus 5 degrees Celsius across a 4-hour heating cycle. The margin for error had effectively been eliminated. Thomas Brennan was a furnace operator at the Alcan facility in Banbury, a man of 46 years who had been heating aluminum since before most RAF pilots were born. He had developed what colleagues called furnace sense, an almost intuitive understanding of when a batch had reached optimal temperature. When the color of the flames indicated precise conditions, when the behavior of the metal itself suggested readiness for the next stage of processing, Brennan's sense had served him well for 2 decades. It had kept him employed through depression, through the chaos of mobilization, through the constant pressure of wartime production demands. But furnace sense was an analog skill in an increasingly digital age. The new protocols required thermometers, written logs, official documentation. A man's intuition, no matter how accurate, could no longer be trusted. The orders came down through official channels in early March. New temperature monitoring equipment was installed. A technical supervisor was assigned to oversee the protocol implementation. Workers were given written instruction cards detailing each step of the revised heat treatment schedule. Deviations were to be reported. Anomalies were to be documented. The furnace operators were no longer artisans. They were components in a larger system. Brennan accepted this with the stoicism of a man who understood that war had already transformed everything. He learned the new procedures. He followed the written instructions. But on the 4th day of the new protocol, something went wrong. A batch of aluminum wing panels was being heated according to specification when one of the new thermometers failed. The gauge simply stopped registering temperature. Without instrumentation, Brennan had no objective measure of the furnace's state. He faced a choice: stop the batch and report the equipment failure, or use his judgment to determine if the heating was proceeding correctly. Brennan looked at the aluminum in the furnace. The color was correct. The behavior of the metal, the subtle way it seemed to glow as it approached optimal temperature, matched his 30 years of experience. He made a decision that seemed logical at the time. He continued the heating cycle. The batch emerged from the furnace and proceeded to the next stage of processing. It was only 2 weeks later, when these panels had been incorporated into Spitfire wing structures and subjected to final stress testing, that the anomaly became apparent. The resilience characteristics were degraded. The cyclic loading test showed cumulative fatigue, the very failure that the new protocol was designed to prevent. The batch was rejected, production was halted, an investigation was initiated. Harcourt was notified immediately. The failure represented a potential breakdown in the entire program. If the heat treatment protocol was unreliable, if it was dependent on factors beyond current control, then the entire strategy was compromised. He traveled to Banbury on a grey March afternoon. The facility was a sprawl of brick buildings and industrial chimneys, the air thick with the smell of hot metal and mineral oil. Brennan was waiting in a small office with 2 managers and a technical supervisor. The atmosphere was one of controlled crisis. Harcourt listened as the events of 4 days earlier were reconstructed: the thermometer failure, the decision to continue, the use of operator judgment, the failure of the batch. When the explanation was complete, Harcourt did something that surprised everyone in the room. He asked to speak with Brennan alone. In the privacy of the office, Harcourt asked a single question: "How many times in your 30 years of work have you relied on judgment instead of instrumentation?" Brennan's answer was quiet, considered. "Every day, sir. Instruments fail, men don't. But yesterday, your judgment failed," Harcourt said, not unkindly. "Yes, and I'll know better next time." Brennan paused. "The new system, it doesn't account for human judgment. It requires perfection. Humans aren't perfect." Harcourt understood in that moment the profound vulnerability of his discovery. The heat treatment protocol worked in theory, but implementation depended on a chain of human decisions, human machinery, human fallibility. A thermometer could fail. A supervisor could make an error. A factory worker could misread an instruction. Each point in the chain represented a potential failure. The program required not just better materials, but better systems, better training, better accountability. Better integration between human judgment and mechanical precision. Harcourt spent the next week at the Banbury facility, working with Brennan and the technical supervisors to develop redundant measurement systems and decision protocols that preserved operator expertise while removing dependence on individual judgment. Multiple thermometers were installed. Cross-checks were built into the process. The written instructions were revised to clarify decision points where judgment might legitimately vary. Most importantly, Brennan and operators like him were given genuine authority over the process. They were trained not just to follow instructions, but to understand the metallurgical principles underlying those instructions. When instruments conflicted, operators had clear protocols for resolution. Human judgment was no longer eliminated. It was integrated into a system that acknowledged both its value and its limitations. The revised protocol was implemented across all British aluminium production facilities by June 1943. The failure rate dropped to less than 2%. Production accelerated. By autumn, the first Spitfire squadrons equipped with heat-treated aluminum began combat operations. The results were measurable. RAF pilots reported improved sustained turn performance. Aircraft endurance in combat operations increased by approximately 15%. By early 1944, the performance gap between British and Japanese fighters had been measurably narrowed. But Harcourt never forgot standing in that office with Thomas Brennan, understanding that the crucial factor in his scientific discovery was not physics or chemistry, but the wisdom of a man who had heated aluminum for 30 years and understood in his bones when a material was ready. The Teacup had suggested a principle. The factories had to believe it. By the summer of 1943, Harcourt's discovery had become embedded in British aircraft production. The new heat treatment protocol was operational across 6 major manufacturing facilities. Over 2,000 Spitfires and Hurricanes with the modified aluminum had entered service. Performance improvements were documented, verified, and classified as restricted intelligence. But Harcourt began to withdraw. He requested reduction of his responsibilities in July. He cited exhaustion. He mentioned the desire to return to pure research rather than applied engineering. His supervisors, grateful for his contributions and aware of the psychological toll that wartime work could exact, approved the transition. By August, he was no longer required to attend the weekly program meetings. By September, his involvement had been reduced to occasional consultation on technical matters. Margaret noticed the change. In her diary, she wrote, "Edmund seems diminished, not in body, but in spirit. It is as if the war itself has weight, and he has been carrying too much of it alone." The truth was more complex. Harcourt understood by the autumn of 1943 that his discovery had consequences he could not fully contain or predict. The modified aluminum was being incorporated into British fighter aircraft at an accelerating rate. Those aircraft were being flown in combat operations across 3 theaters of war. They were engaging German fighters over occupied Europe, Japanese aircraft over India and the Pacific, Italian fighters over the Mediterranean. The performance improvements he had enabled were resulting in measurable increases in RAF combat effectiveness. But effectiveness in war meant destruction. It meant pilots, British, German, Japanese, Italian, American, Australian, being killed more efficiently because the materials science had advanced. His Teacup revelation had not prevented death. It had merely changed the calculus of how death was distributed. In October, Harcourt received a letter from Dr. James Schaefer, a German metallurgist whom he had known professionally in the 1930s, before the war had severed scientific community across national lines. The letter had taken months to arrive, routed through neutral Sweden, its envelope marked with the stamps and seals of multiple intelligence services. "My dear Edmund," the letter began in careful English, I do not know if this communication will reach you. I write it with the knowledge that it may be intercepted, read by officials, perhaps used as evidence of something it is not, but I must attempt the communication. You have made a discovery regarding the heat treatment of aluminum. I know this because we have also made this discovery. We have examined 0 components recovered in North Africa. We have reached conclusions identical to yours. We are implementing the protocol into Messerschmitt production. I write this not to threaten you, but to suggest something you may not yet have considered. The same knowledge exists on both sides now. Your advantage will be temporary. The material intelligence will diffuse. Within 2 years, perhaps 3, all major air forces will be implementing versions of this protocol. The margin you have created will close, but the knowledge itself will remain. And so I want to ask you something that I suspect troubles you. Were we correct to pursue this knowledge? Has the war become more efficient? Has more technology made it more moral, or merely more devastating? I remain, despite the war, your colleague in uncertainty. The letter was signed with Schaefer's name and the date of composition, March 1943. Harcourt never responded. He could not have, even if he had chosen to. The letter would have been intercepted by British intelligence. Communication with enemy nationals was forbidden, but he kept the letter, hidden in a locked drawer beneath his desk, and he read it periodically during the months that followed. Schaefer's question haunted him because it was not rhetorical. It contained a genuine epistemological problem at the heart of technical war work. Knowledge, once acquired, could not be unacquired. The heat treatment protocol would eventually be understood by all combatants. It would become standard practice. The advantage it conferred would be temporary, but the underlying principle that material science could alter the efficiency of destruction would persist. In November 1943, a memo crossed Harcourt's desk requesting his input on a new project: the acceleration of aluminum heat treatment protocols for tank armor. The same principles that had improved fighter aircraft performance could, theoretically, be applied to armored vehicles. The proposal was for a rapid research program, 6 months duration, with implementation projected for 1944. Harcourt was asked if he would lead the program. He declined. He submitted his letter of resignation 2 days later, citing medical reasons that were technically accurate. He had developed what his physician called nervous exhaustion. The diagnosis was vague and acceptable. It permitted him to withdraw from classified work without requiring detailed explanation. By the new year of 1944, Edmund Harcourt had returned to civilian status. He was assigned a position at University of Cambridge as a research fellow in materials science. The university had been partially repurposed for war research, but it maintained the fiction of academic normalcy. He was permitted to conduct theoretical research in metallurgical physics, unclassified work that would not advance any particular military objective. He spent the remainder of the war years studying the properties of crystalline structures in non-ferrous metals. His publications were sparse but meticulous. They made no reference to heat treatment protocols or aircraft applications. They were pure science, disconnected from the machinery of war. But in the evenings, he continued to read reports of RAF operations. He noted casualty figures. He tracked aircraft performance metrics. He understood with perfect clarity that the Teacup revelation had provided a measurable advantage that had resulted in Allied victory being accelerated by months, perhaps years. He also understood that this acceleration had saved lives, British lives primarily, but also the lives of civilians in occupied territories who would have suffered longer under German rule, the lives of Americans and Soviets and Chinese whose wars might have ended sooner as a result of earlier overall victory conditions. But the knowledge remained unchanged. Technology had made destruction more efficient. The moral weight of that efficiency could not be resolved through technical calculation. In the spring of 1946, more than a year after the war had ended in both theatres, Harcourt received a visitor. The man was Captain Michael Davies of RAF Intelligence, a youthful officer with the precise manner of someone trained in official communication. Davies brought a package. "Dr. Harcourt," the captain said, presenting the object with formal courtesy. This artifact was recovered from the Imperial Japanese Army Air Service facility at Nagasaki during the American occupation. It has been classified and archived for the past year. However, as part of the post-war scientific survey, certain objects have been declassified for return to relevant researchers. The package contained a wing panel section from a Mitsubishi Zero. It was perhaps 20 centimeters in length, a curved piece of aluminum alloy that had survived the war and the occupation. The metal bore the marks of service: slight corrosion, a small dent near the leading edge, the subtle wear patterns of years in combat operation. Davies explained, "This particular aircraft was recovered from the wreckage of a downed Zero in Burma, 1942. It was the specimen from which you drew your initial analysis. The Japanese Navy has requested, through post-war liaison channels, that this artifact be returned to Japanese custody. However, the Air Ministry thought you might want to examine it one final time before repatriation." Harcourt held the aluminum panel carefully. It was heavier than he expected. The metal bore the weight of history, of the Teacup morning when he had first theorized about stress distribution, of the laboratory tests, of the factory protocols, of the thousands of aircraft that had been manufactured according to specifications derived from understanding this very material. "Did you know," Harcourt said quietly, turning the panel in the light, "that the Japanese engineer who designed this heat treatment protocol was killed in an air raid on his factory in 1944. The Americans bombed the facility. The facility was destroyed. The engineer was among the casualties." Davies did not respond. He had clearly been briefed on this detail. "I never knew his name," Harcourt continued. "I still don't know his name. But I know that he reached the same conclusions I reached. He understood material science. He understood crystalline structures. He understood the principles of resilience and stress distribution. And we both applied this knowledge to make aircraft that could kill more efficiently." He set the panel on his desk. "I could theoretically examine this panel again. I could conduct new tests with post-war equipment. I could publish a technical analysis of Japanese heat treatment methodology. It would advance science. It would be valuable work." He paused. "But I cannot do it, not because the knowledge is forbidden or because the war has ended, but because I understand now that some knowledge, once acquired, carries an irreducible moral weight. The Teacup showed me a principle. The principle led to methods. The methods led to machines. The machines led to deaths. On both sides, countless deaths where the margin between survival and mortality was altered by fractional improvements in material efficiency." Davies listened with the professional expression of someone trained in diplomatic silence. "Please tell the Air Ministry," Harcourt said, "that I decline to conduct further analysis of this artifact. And please tell the Japanese government, if such communication is permitted, that their engineer was brilliant. His work survives. And like all brilliant work that serves military purposes, it will be remembered with both pride and sorrow by whoever understands what it enabled." The Zero-wing panel was repatriated to Japan in June 1946. It was eventually housed in a museum in Tokyo, catalogued as a specimen of wartime aircraft engineering. A small placard identified it as a component from a Zero recovered in Burma, 1942. No mention was made of the British scientist who had studied it. No indication was given of the Teacup revelation that had emerged from contemplating its properties. Harcourt returned to his work in pure metallurgical theory. He published 17 papers between 1946 and 1952, each advancing scientific understanding of crystalline structures without any reference to military application. His colleagues noted that his work had become abstract, theoretically elegant, but disconnected from practical engineering. One colleague wrote in a letter, "Edmund has become a philosopher masquerading as a physicist. He asks beautiful questions to which he refuses to provide applied answers." But Harcourt knew the truth. He had provided applied answers, and he would spend the remainder of his life understanding the cost of those answers. In 1963, 17 years after the war had ended, a small article appeared in a metallurgical journal published in Japan. The article, written by Dr. Takeshi Yamamoto, provided the first post-war technical analysis of Japanese heat treatment protocols used in Zero aircraft production. The article acknowledged the convergence of British and Japanese research, how both nations, independently and simultaneously, had reached identical conclusions about the principles of resilience in aluminum alloys. Harcourt read the article with a profound sense of completion. Yamamoto's research confirmed every aspect of his own understanding. The Japanese engineer, whose name Harcourt finally learned in that moment, had been precise, methodical, and brilliant. The work had represented the pinnacle of applied materials science in wartime context. Harcourt carefully preserved the article. He placed it in an envelope with a handwritten note and sealed it with instructions that it be opened only after his death. The note read, "The teacup holds the answer, but the answer cannot be unlearned. Those who seek knowledge in service of war must understand that the knowledge itself survives the war. It becomes testimony to both human ingenuity and human limitation. We make things more efficient at destruction, and then we must live with what we have created." Edmund Harcourt died in 1971. The envelope was opened according to his instructions. His legacy, ultimately, was not the aircraft he had indirectly improved, but the recognition that technical knowledge carries moral dimensions that extend far beyond the immediate application. The teacup, had anyone asked, would have said nothing. It would have only held heat, as all material things hold the weight of what passes through them, visible and invisible, destructive and creative, understood and forever mysterious. Subscribe to our channel to explore more cases and curiosities from World War II. Thank you for following the story. See you in the next video.